For this example, we're looking at a rigid bar, which is connected back to ground by these three rods of 1, 2, and 3. We know all of the properties of the rods. We know their lengths, we know the cross-sectional areas, their Young's moduli, their coefficients of thermal expansion. What we know is the temperature of 1 is held a constant, whereas 2 and 3 are each raised by the same delta T in temperature. What we want to do is determine the rod stress that we see for 1, 2, and 3. What we're going to do is begin with our usual first step, and that is static equilibrium. We'll draw a free body diagram of that rigid bar. And the forces that you're going to have in that rigid bar are going to be the loads that are carried by these three rods. So we have the load carried by rod 1, the load carried by rod 2, and by rod 3. I'm going to use x to the right and y up. This again is point K, this point is B, and this is C. So when I look at the bar, when I sum forces acting in y, I have F1 plus F2 plus F3, and that sum for equilibrium is a 0. I'm going to write a moment equation about the left end there of K, which is going to give me F2 with a moment arm of 2L. It's going to be in the plus K. I have F3, which has a moment arm of 4L. It's going to be a plus K. And that is equal to 0 for equilibrium. So we got 1, equation 2. So we have from equilibrium, we have only 2 equations, but we have 3 unknowns. We have the member loads there of F1, F2, and F3. So what this means is that the problem is indeterminate. And all the indeterminate means is that we need to take into account deformations in order to provide the additional equations that we need to solve for our unknowns. So now let's look at our elongation equations. The elongation equations are the E1 is equal to F1 times L1 divided by EA plus alpha delta T. Well, it says that 1 is kept at a constant temperature here, and L1 is simply equal to L. E2. E2 is load carried by member 2 times L2 divided by EA plus alpha delta T. In this case, it says here that L2 is a length corresponding to 2L. And E3, F3, L3 divided by EA plus alpha delta T. Again, 2 and 3 are raised, or their temperatures are changed by the same amount there of delta T, and L3 here is also equal to 2L. So that gives us 3 more equations, 3, 4, and 5, but as we look at the scorecard here, we have also increased the number of unknowns by the same amount. So there's no net gain yet. But where we get the final equations that we need are going to be the compatibility. The compatibility in this case is we have to keep in mind that these 3 rods are connected to the same rigid bar. So the picture that's given to us here shows the deformed state of these joints there of K, B, and C. K star, B star, and C star. So UK is given by this amount here. The deflections there for B, that's UB. And then the deflection there for C, that's UC. What we need to do is look at how these deformations give rise to its change in rotation for that bar. So this amount here is going to be UC minus UB. I'm sorry, this is UC minus, correction there, UK, where this amount here is UB minus UK. So it's going to be the relative displacements between these joints reference back to K. And so what we will do is we'll look at a triangle, right triangle formed by this for small angles, and we'll compare that with this similar triangle which goes like this. And so what I will say here is that UB minus UK divided by the length there of 2L, that must be the same as UC minus UK divided by 4L. Along with the fact that UK is the same thing as the elongation of 1. UB is the same thing as the elongation of member 2, and UC is the elongation of member 3. So we have introduced no more unknowns, but we've also introduced an additional equation. So the solving part in this case is we need to solve equations 1 through 6 for the 6 unknowns. And the 6 unknowns are going to be the member forces there of F1, F2, F3, the elongations of E1, E2, and E3. 6 equations for 6 unknowns. In review, what we have here is this rigid bar which is supported by 3 rods. So that's an indeterminate situation. We cannot find out how much load is carried by each one of those rods because we have too few equilibrium equations for the number of unknowns. So we pick up our additional equations by looking first at the elongation. That relates the change in length of these reference back to the loads and the temperature change. And then we have a compatibility equation which basically says these rods are connected to a rigid bar, and so this is a rigid bar rotation assumption right here. Coming from the picture, it's a statement of similar triangles, but that's all based on the fact that that bar there of KC is rigid and doesn't bend.